Hey everyone, and welcome. Today, we're going to dive deep inside your computer to unpack one of its absolute cleverest tricks, how it manages to juggle dozens, sometimes hundreds of tasks all at once. So, let's get right into it. Just think about it for a second. You've probably got a web browser open with who knows how many tabs. Maybe some music streaming, a document you're working on, plus all those invisible background processes just humming away. How in the world does a single CPU core handle all that at the same time? It feels like it should be impossible, right? Well, it's not magic. It's just a really, really smart illusion. The secret sauce here is something called CPU scheduling. And to really get our heads around it, let's use a fun analogy. Picture your computer's CPU as this single world-class barista who can make any drink you can imagine at lightning speed. And all your programs, your browser, your game, your music app, they're all just customers standing in a long line, each with a different order. The scheduler? That's the coffee shop manager, deciding who the barista helps next. Okay, so here's the more textbook definition. The operating system, our manager, is constantly looking at this line of programs, which we call the ready queue, and it picks one to give to the CPU, our barista. And this whole decision-making process, it happens thousands, even millions of times every single second. It's insane. All right, so these schedulers basically come in two main flavors. A non-preemptive one is like a barista who, once these start making a customer's super complicated 10-drink order, has to finish that entire order before they can even look at the next person in line. A preemptive scheduler, on the other hand, is way more flexible. It can start that big order, but hey, if someone pops in just needing a quick espresso, it can hit pause, serve that quick customer, and then get right back to the big order. This is a really crucial difference. Okay, so if we're the manager of this coffee shop, how do we even know if we're doing a good job? What makes a scheduling strategy successful? Well, before we can look at the different strategies, we need to know how to keep score. Well, it really boils down to 5 key things you're trying to juggle. First, you want to maximize CPU utilization. You want your barista working, not just standing around. You also want to maximize throughput, how many customers get served per hour. Then you want to minimize 3 things. Turnaround time, which is the total time a customer is in the shop from start to finish. Waiting time, the boring part, just standing in line. And finally, response time, how fast a customer gets that first sip of coffee, even if their whole order isn't ready yet. It's a huge balancing act for sure. All right, we know the rules of the game. Now let's meet the players. We're going to check out a few of the core scheduling algorithms, each one with a totally different game plan for our barista. First up, we have the most intuitive one, first come, first served. It is exactly what it sounds like. Whoever gets in line first gets served first. Simple, seems fair on the surface, and it's super easy to set up. But you gotta ask, is it really the best way to do things? So let's put this to the test. Imagine 3 programs or customers show up. P1 is a huge order that's gonna take 24 milliseconds. P2 and P3 are tiny, just 3 milliseconds each. Well, if P1 gets in line first, P2 has to wait the full 24 milliseconds, and poor P3 has to wait 27. The average wait time here is a painful 17 milliseconds. For P2 and P3, that's an eternity to wait for such a tiny job. But now, just watch what happens if they arrive in a different order. Let's say the 2 small jobs, P2 and P3, get in line first. They get served super quick. P1 still takes its 24 milliseconds, but it just waits behind them. Now look at the average waiting time. It drops from 17 all the way down to just 3. It's the same exact jobs, the same scheduler. The only thing that changed was the arrival order. And look at that difference. And this right here, this is a perfect example of a classic problem with first come, first served, called the convoy effect. It's just like being stuck behind a giant, slow-moving truck on a 1-lane road. All the fast little cars, or in our case, the short, quick programs, get completely stuck, and the efficiency of the whole system just tanks. So naturally, this leads to the next logical idea. Let's call it shortest job first. The strategy is brilliant in its simplicity. To avoid that convoy effect, our barista just looks down the line and always picks the customer with the fastest order. And mathematically, this is proven to be the optimal strategy. It will always give you the absolute minimum average waiting time. It sounds perfect, right? The ultimate solution? So what's the catch? Because there's always a catch, isn't there? And this one's a doozy. How in the world does the scheduler know, ahead of time, exactly how long a program is going to need the CPU? It's like asking our barista to be a mind reader. Basically, it requires the scheduler to be a fortune teller.
And that's the fundamental trade-off with shortest job first. On one hand, it is provably the absolute best for minimizing the average wait. But on the other, it's impossible to implement perfectly in the real world because we just can't predict the future. It's this beautiful, perfect theory that just smashes into the wall of reality.
So a more practical idea is priority scheduling. In this system, every program gets a priority number, kind of like a VIP pass. The scheduler always ignores the line and serves the customer with the highest priority first. This is great for making sure your really important system tasks get done immediately. But this system has a potential dark side. A low-priority job could end up waiting forever if a steady stream of high-priority jobs keeps showing up. We call this starvation. Okay, so what if we prioritize fairness above all else? That brings us to our next strategy, round robin. The big idea here isn't to finish one customer's order, but to give every customer a little bit of attention in a cycle. Each program gets a tiny slice of CPU time called a time quantum. So our barista might work on one order for 1 minute, then immediately move to the next person for 1 minute, and then the next, cycling through the entire line over and over. Let's see how this plays out with our old set of programs, using a time slice of 4 milliseconds. See how it works? First, P1 gets 4 ms. Then, boom, the scheduler switches to P2, which needs less than 4, so it just finishes. Then, boom, we switch to P3, and it finishes too. Only then do we cycle all the way back to P1 to give it another slice and another until it's done. Now, the total time to finish everything might actually be a bit longer, but who cares? For things like moving your mouse or typing, that super fast response is what makes your computer feel snappy. So we've got these different strategies, right? Each with its own pros and cons. But in the real world, modern operating systems are way smarter. They don't just pick one. They use incredibly clever hybrid approaches to try and get the best of all worlds. Enter the multi-level feedback queue. And trust me, this is where things get really clever. Imagine this. A new program comes in. It starts at the top, in the VIP line, the highest priority queue. It gets a very short time slice, using round robin. This is perfect for quick, interactive tasks. But if it uses up its time and isn't done, it gets demoted to a lower priority queue, which has a longer time slice. If it's a really long, heavy-duty job, it'll eventually trickle down to the bottom queue, which is just a simple first-come, first-served line. It's a system that actually learns and adapts. It's just brilliant. Okay, so we've been talking about all this theory, but why does any of it actually matter to you? Well, because these seemingly abstract ideas are running constantly, every single second, right inside the devices you use every day. Well, think about the device you're watching this on right now. It probably has multiple cores, right? That makes scheduling even more of a high-wire act. The OS doesn't just have to decide which program to run next, but which core to run it on, all while trying to squeeze out every drop of performance and, maybe even more importantly, not destroy your battery life. And really, that brings us to the core trade-off that's happening on your phone every single second. What do you value more? That lightning-fast, snappy response when you open an app, or having your battery last the entire day? The scheduler is the one making that tough call, constantly balancing performance against power. Millions of times a day, all thanks to the hidden art of CPU scheduling. Thank you so much for watching. If you found this explainer helpful, go ahead and hit that like button, share it, and of course, subscribe to Tech Talk 101 for more deep dives into the technology that shapes our world. We'll see you in the next one.